We talk about the history and future of antibiotics because, well, the history helps us understand the present, and the future is what we need to work on a lot. So we get into it. The first antibiotics were dyes. They were colorful compounds that chemists had already made. And so people thought, what the heck, let's see if bacteria are susceptible to them. This one is super toxic, 3 arsenic molecules in the middle, but it worked against Treponema pallidum, which caused syphilis. Penicillin, this, I haven't heard of this used recently. I can't look at a molecule and know it's toxic unless it has heavy metals like this in it. But that worked for a while. But those weren't major antibiotics, and they weren't effective enough that people were going to use them against every bacterium and manufacture them in huge quantities. Penicillin was different. Penicillin was active against most gram-positive bacteria, and that would be a lot of the bacteria that would cause wounds in soldiers. So if a bomb goes off somewhere nearby and you're on the battlefield, pieces of dirt get accelerated to extremely high speeds, and they hit you, and the dirt goes under your skin along with any bacterial endospores. And so bacterial infections historically were the most common cause of death among soldiers. So what people realized was if they could develop antibiotics that would protect soldiers who got infections, they could save those soldiers. And so penicillin was a good candidate for that, again, because it worked against most or all gram-positive bacteria back then. Many people discovered penicillin. Many people thought it would be a useful thing, but if they couldn't make big enough quantities of it or purify it well, it wouldn't matter. It's not a drug until you can purify it and put it in a deliverable form that can get to the people who need it. And so the scale up is what we needed to do. And the people who had been working on it in Europe had to stop because that was where the war was. And so the US kind of took over. And there were plenty of strains of the Penicillium mold that made penicillin. The biggest issue, the last big leap that had to be made, was to find a strain of Penicillium that could grow in a liquid culture, so in a giant vat. So this is mold that could grow in a liquid and constantly make large quantities of penicillin while it was growing in that giant liquid culture. And most of the strains they had wouldn't do that. They either wouldn't grow in liquid culture or they wouldn't make a lot of penicillin while they grew in that broth liquid. So this person, again, this is a story that might or might not be true. Mary Robeson was a technician at one of the government labs, and as the story goes, she was tasked with finding more penicillium strains. So she went to, she famously found a cantaloupe that had a penicillium mold all over it. And it was one of many strains she collected, but it happened to have the ability to make penicillin while growing in broth. So this is the strain that ultimately gave rise to all of the descendants that currently make penicillin, and its descendants are the ones that made all the penicillin used in World War II. And World War II, because of that, was the first major war where infectious disease wasn't the primary cause of death for soldiers. Why is this painting in my slides? Well, partly it's a painting that commemorates an important moment in history. You can't really overstate how important it was that people figured out how to mass produce an antibiotic. But also, this painting was hanging in my boss's office because the person who painted it was a famous Wisconsin painter who was partly famous for managing to sell paintings where the faces didn't look quite right. Some of the people he drew just look scary, but they're also like historical artifacts now, so it is what it is. So sorry if you weren't into that. Anyway, on to the next thing. So then, scientists discovered more and more antibiotics for the next 20 years. And then that kind of stopped. If we're not discovering new types of antibiotics, what are we doing? Well, one thing we can do is modify the antibiotics we have. And we've done that. We've taken penicillin and changed it into new forms like methicillin and amoxicillin that have activity against some gram-negative bacteria. And so some of these we'd call semisynthetic, where the mold would make them and then we modify them. Or molds would design them, sort of, and we'd make them and modify them. But pretty much as fast as we can make them, bacteria will become resistant to them. And this is a process of accumulating mutations that change the target inside the cell. And if those happen to be on a plasmid, they can be easily shared through horizontal gene transfer. And so this is what we saw was penicillin was introduced on a wide scale in 1941, and penicillin resistance started showing up shortly thereafter. Methicillin was the big exciting new derivative of penicillin that could treat penicillin-resistant bacteria. And that's when we started to see methicillin-resistant Staphylococcus aureus. And these bacteria kind of got worse and worse. Around the 2000s is when the horizontal gene transfer events combined MRSA with vancomycin-resistant enterococci to get vancomycin-resistant Staph aureus. So these were resistant to all the penicillins plus vancomycin, which was the backup treatment against MRSA. So this is just something we expect to see happening. It's not a question of will resistance happen for a given antibiotic. It's when will resistance happen and how widespread will it be? And that's our opportunity, is to slow this down and make sure that antibiotic resistance against a given antibiotic isn't widespread. That's what we try to do. This link goes to this video. It's a YouTube video. Watch Antibiotic Resistance Evolve, Science News, in the Science News channel. Science News is a magazine that does like news from the world of science. And this was a super cool, amazing experiment some scientists did with a giant petri dish. Well, it's complicated, but basically they forced E. coli to develop mutations until it was extremely resistant to an antibiotic, and they could study the process. I highly recommend you watch the video. It's short and it's amazing. This is an example of one of the newer antibiotics. It's a new class of antibiotic, and it's the only one since the 1960s that is brand new. We just don't expect this to happen again. The big pharmaceutical companies, they don't have a big financial incentive to find antibiotics. They make their money by selling antidepressants and blood pressure medication, things that people take every day forever. Those are profitable drugs. Antibiotics are not. But these companies need to do some marketing. They can't afford to have everybody hate them, so they will do things like try to discover antibiotics. They put millions of dollars into searching for antibiotics, knowing that they wouldn't be profitable. And using some of the best techniques anyone could imagine, they searched the world. They looked all through all the soil they could get. They looked through all the ocean water they could get, wherever they could study bacteria and fungi and search them for making new antibiotics. They did, and they gave up eventually. So we no longer think we're going to find a new strain of mold or bacteria that's going to make a new type of antibiotic. The pharmaceutical companies searched the world, and no university lab has the kind of resources to do anything that these big drug companies didn't already do. So university labs are doing clever, creative things, trying to find the new antibiotic. But we can't assume that they will. We can't assume that any new antibiotic will ever appear that will be widely useful. So we have to operate under the assumption that we've already discovered all the antibiotics we will ever discover, and we need to maintain their efficacy. And so we're going to get into that. We're going to start looking in the next video at cell wall synthesis inhibiting antibiotics, starting with penicillin, and then we'll look at the penicillin derivatives and then the other related antibiotics. And we'll see some resistance profiles, and you'll get all that terminology. And so from here on, we'll be learning about specific antibiotics and the context around them, instead of kind of the general ideas I've been using so far. So I will see you there.